Last couple of chapters we looked at have had to do with sampling. This chapter, chapter 6, has to do with how good of a job we've done with our sampling. So if you look at the notes, one of the things that we first come to is something called sampling error. And basically what this means is any time that we take a sample from a population, there's a chance, and actually a 100% chance, that the sample would not look exactly like the population. The difference between these two, between the sample and the population, how far off these are, is called sampling error. The couple of factors influence this. This is important to remember. One, the sample size affects the sampling error, and two, the quality of job that you do with sampling in terms of doing a stratified random sample versus just a random sample. Those factors influence the sampling error. One of the questions I often is asked, as we had mentioned before, was how big of a sample do you need? Does it really matter? Well, yeah, it does. And related to this is it better to have 300 non-random participants or 50 random participants? Well, as you can see from this graph, as you start getting more and more people in your sample, you're going to start reducing your sampling error. And this stays true for most conditions. Now, all things being equal, if you had 300 random versus 300 non-random, the random would be better because that has to do with the type of sampling that you do. So first of all, sample size makes a big difference. All things being equal, the type of sampling that you do or quality of sampling that you do makes a big difference. So there's a couple. The next thing we're going to look at is something called the standard error of the mean. And to illustrate this point, I'm going to show you a document that you have in your content folder. Let me blow this up a little bit. Let's assume for just a minute that we have a population that we're trying to say something about by using this sample. And generally what we do is we take this small sample that's supposed to represent this large population. So let's assume for a minute that the population mean is 35. Well, when we take our first sample, without knowing what the population mean is, we get a sample that is 39. Its mean is 39. Assume for just a moment that we could take another sample, and if we were to do that, we might get a situation where the mean is 31. So now we have one group that was 39. Assuming we could do it again, we'd have another group that's 31. And if we did it a third time, we might actually get a sample where the mean is 35. If we did it again, we might get another sample where the mean is 32. And what is happening is, theoretically, over and over and over, this thing has done a sample. And it starts to develop a normal curve based upon these samples where you have a mean and standard deviation. A standard error of the mean basically means that it is estimating, were you to do this over and over and over again, what your score is and how far off you are from what the population mean really is. What you have to remember is we don't ever really know what the population mean is, because if we did, we wouldn't need to do this. We're making an estimate of the population mean by using this standard error. A small standard error measure should indicate that if we were to take another sample, we'd get something very similar to what we got this time, and therefore the samples would look similar and would look like the population. If the standard error of the mean were very large in comparison to the mean, then we assume that if another sample were taken, this sample would look very different. And each sample from there on out would look very different as well. So a large standard error of the mean, or large SEM, indicates a poor job of sampling, and a small SEM indicates a very good job of sampling. Some places where you can see this are in your book. If you have the most recent copy of this, it is on page 130. If you look in excerpt 6.1 in your book, It has an SEM and it has just a plus or minus 5.3 next to the heart rate. If you look at excerpt 6.2, you have a standard error of the mean for each of these characteristics. So looking in table 6.2, you have women and men. You have 77 women, 72 men. Their age for the women is 48.7. Their standard error of the mean is 1.2. So that means that if they were to do this sample again, they would get anywhere from, 47.5 years old to 49.9 years old. That's the standard error of the mean. So you can kind of get a picture of what all those look like. The other way that people do this is if you look at excerpt 6.3, you'll see a bar graph with what's similar to a box whisker plot. And basically what this shows is what the mean is and how much error there is in that mean. Basically it kind of gives you a range. So the shorter that line is at the top of that box in excerpt 6.3, the shorter it is, the less error you have and the better job you've done representing that population. The most important point to remember from this is the SEM is a representation of how well the sample looks like the population, regardless of how they portray it. And you can see another example in 6.4. It's an estimate of how good of a job you've done with this. The next thing to look at is something called confidence intervals. And this one's a little bit more difficult to understand, but it is also a little more common. It's a determination of how well the sample represents the population or how different the statistic is from the parameter. This confidence interval, this 95% confidence interval, means if you were to assume that if many samples were taken from the population, 95 times out of 100, your sample will fall into the parameter. I mean, if you're to do this over and over and over, 95% of the time, the number that you're seeing at any particular point would fall within the range that they're going to give you. And you have to be able to see some examples of this to understand it. It's a range where you expect something to be. By saying expect, we leave open the possibility of being wrong. The degree of confidence measures the probability of that expectation to be true. I want to put an example of this in the discussion board. It's called Coke or Pepsi, and this is an example of how confidence intervals work. So you need to go to the discussion board, take a look at this example, and you're going to see how confidence intervals, how sure we are about them, and how wide these confidence intervals are, how those two things interact. It's a lot easier to see it on a table like that rather than trying to get it through here. This will end this Chapter 6 Part 1 video.